this is the domain I'm studying. I'm supposed to have 3 thermoelectric generators I want to cool. The location of the thermoelectric generators are on this surface. On the thermoelectric generator, I use a spreader. This is a spreader. This is a rectangular body is a spreader to spread the heat at a larger surface. And above that, there is 3 heat sinks to dissipate the heat furthermore. Okay, this is the case I'm studying. And here we have, this is the fluid domain surrounding the heat sinks. This is natural convection. So, and the heat sinks are surrounded by ambient air. There is no, the surrounding doesn't have specific dimensions. This is the ambient air, it's very big. So I choose part of the surrounding, which is this body, to represent the surrounding domain.
What is the
dimensions should be theoretically is infinity. But I use some thickness and then enlarge this size furthermore. This is 60 millimeter. I should study 70 millimeter, then 80 millimeter, until I reach a point that no change in results.
Yes.
So theoretically it should be infinity, but I use some dimension very large and increase it furthermore until I find that it is not affecting the result. Okay. So this I think this one is like this 280 millimeter, and the height is 680 millimeter. Okay, but you should increase this after reaching a stable solution. Increase it furthermore until you reach the solution to be stable and no change in it in the results. The thickness is 60 millimeter. This will not, I will not change, because I'm studying here only one column of 3 TGs. There is supposed to be another column to the right and another column to the left. So I only study one column and will consider this surface to be symmetry. Okay? This surface symmetry surface and this is symmetry surface. So I will not change the width here. Okay? Is this clear? Okay.
They are heat sink.
The heat sink.
3 heat sinks.
Yes, 3 heat sinks.
There is no thermoelectric generator.
The thermoelectric generator is not in this model. I'm not studying the thermoelectric generator itself. I'm studying the heat dissipated from it, which is supposed from this side. Yes, this side. This is the side on which the thermoelectric generators will be fixed. I have an equation for the flux. I don't need to simulate the thermoelectric generator itself. Now, after creating this model, which I will not talk about in the design modeler, you can create the model in any program, design modeler or anything else. You will find that here I have 5 bodies. This is spreader, heatsink 1, heatsink 2, heatsink 3, and the surrounding. Okay? Each body here is independent of the other. If I left everything here as it is, every body will be independent to the other. That means that if I meshed I can show you here, if I meshed, I will mesh the heat spreader. Okay? And I will mesh the heat sink. What is this? Give me a second. I will tell you more detail about this, but now I'm trying to show something. Now look at this. The mesh on the heatsink is separated from the mesh on the spreader. They are not connected. This happens because in the design modeler, I left everybody is separated from the other. I didn't collect them in a single part. So bodies are separated completely and independent to each other. And the mesh created on each one of them will be separated from its adjacent cell or adjacent body. Okay? To solve this problem, I need to collect the bodies in a single part, like this. If I click on all 5 bodies here and right click, choose form a new part. This way, When I create a mesh on a body, it takes in consideration that there is a adjacent body, and if there is already mesh there, it will be connected to each other. Okay? This causes a problem. When the body is complicated, like in this case, we have fluid domain and solid domain, it is very complicated and hard for the program, for the mesher to create a mesh in the fluid domain which connect with the mesh in the solid domain. You will find it very hard to achieve this and to achieve it in a good way. You can create a tetrahedron mesh or mesh in a rectangular way, but it will be not efficient. So we need to overcome this challenge to create a mesh which is good with low number of elements, and at the same time we have to the mesh at these surfaces must be connected. I found a solution for this. You can continue in this way by collecting all bodies in a single part, but I find it very hard. I couldn't achieve a good mesh in the fluid domain using this method. If I collected all bodies, the fluid and solid, in a single part, I couldn't achieve a good mesh in the fluid domain. So I collected the bodies of the solid domain only in a single part and left the fluid domain in a separate part. Of course, this means that the mesh will not connect at each other at the interface between them. But the mesh is very fine, and the Fluent can handle this. There is something in Fluent called interfaces which handle this I don't know how the word, not connected mesh. This Fluent can handle this. If the mesh is good and very fine, the error will be very small. You can find that at the solid surface the heat transfer is 10.9 watt, and on the fluid side you may find it 10.89 watt. There is a 1% error or more or less. Do you know what I mean? So this way I can create mesh in the fluid domain which is very good and efficient with very error. I can very small error. Okay. So here I will right click, explode board, separate them from each other again, and select only the solid domain, form a new part, and leave I leave here the fluid domain as a separate part. Okay. This way I find it more efficient in creating a mesh for the fluid domain. Okay.
Will you define a new connection between
yes.
fluid and
yes.
The interface.
Yes. The interface is defined for you automatically in the mesh. I will show you later. But I delete this definition and define it myself because to be more sure about the definition. Because sometimes it get it wrong.
You define it in the mesher or in Fluent?
I start from the meshing application, then I define it in Fluent. I will show you the steps. Okay.
If I didn't define the interface between the solid and fluid, ANSYS can automatically handle this?
It will define it automatic for you.
Okay.
It will do it automatically.
So you don't have to
No.
do anything in it?
No, you don't have. But I
Fluent?
and Fluent will do it automatically for you. But I try to do it myself to be sure about the naming, because Fluent uses another names we will not understand, and to make sure that everything is good, because sometimes it takes the wrong surfaces at the interface. So I do it myself, but Fluent will do it automatically.
Okay. So if you do it with yourself, you start from mesh.
The meshing application, we define it in the meshing application, yes. Now I want to. Okay. Now, as you can see here, the spreader. This is the spreader surface. There is supposed to be here the square surface of a 3 thermoelectric generator, TEGs. But as you can see, this is single surface. In Fluent, I need to define a surface, so I click on it and define the flux, the temperature, whatever it is. But I don't have a surface for the thermoelectric generators here. Okay, so I need to imprint a square surface which represent the surface of the TEG. Okay, this is a small step in design modeler. I will show you how to do it. I need there is something called imprinting. It's like taking a solid body and touching another body, so I form a surface of intersection. This is imprinting. I don't draw anything else. I just tell the programs I want to imprint an edge on the surface that's already exists. So I can use the edge of the. As you can see here, these are the edges of the heat sink. 4 edges of the heat sink. You can see them? See them? The 4 edges which represent the base of the heat sink. I will imprint these edges on the surface, on the bottom surface of the heat spreader. Do you understand what I want to do? So create or tools connect قصدك؟ لا. Projection, yes, projection, no, projection. Tools, projection, edges on face, I select type edges on face. The edges I already selected, the 4 edges of the heat sink, and the target is the bottom of the heat spreader, and generate. As you can see here, I separated a small surface which represents the cold side of the thermoelectric generator, at which I will define the heat flux. Okay. Now I will edit this. I will edit it to include the all 3 heat sinks, the edges of all 3 heat sinks. So I select here this and this.
This step to specify a specific area with a specific property.
To separate a small part of the big surface at which I can define a boundary condition.
But if we separate this area in design modeler, in the sketch,
Yes,
it can
can be done. Yes.
Can be done.
Yes.
But this step can be used if I use if I need the intersection of the projection for specified bodies. Like this step.
Yes, I need an intersection between the spreader and the thermoelectric generator, which should be there. But I don't need the heat, the thermoelectric generators. I will not study the thermoelectric generators.
You only.
I need the intersection only.
You put the effect of thermoelectric generator.
Yes.
And the new imprinted area. You can handle it with the new name and
Yes.
a new service.
Yes, I can give it a boundary condition.
Boundary condition.
If you know how you calculate the heat flux for each thermal, صح?
Yes, I have an equation for heat flux for each
So
thermoelectric
why
generator.
you use the spreader as a phase, and in the fluent you use the boundary condition to calculate the phase flux over.
No, in the heat spreader is adiabatic. No, this surface has no flux at all. This surface has flux coming from the TEG. So I need to separate them.
Yes. Will only make flux on this area.
Yes, the flux is on
This area.
these 3 areas only.
Okay, and what is the function of the spreader?
What? The function of the spreader is to separate the temperature of a larger area,
Okay.
which is the heat spreader,
By conduction.
by conduction. Yes.
What about the convection and radiation?
What about them? We will.
Surrounded area, around this area.
This is the fluid domain, which
No. From the outside.
no, all of this surface is adiabatic. This and this is like a chimney on which the spreader is fixed. The chimney is treated as an adiabatic surface.
And have a certain temperature.
No, it's adiabatic. It's flux equals 0. I don't know the temperature.
Temperature will depend
Whatever
on
it is,
the fluid.
it will be dependent on the fluid temperature.
Yes.
But it is adiabatic. The flux is 0. What do you want to ask?
Okay. I just said if we don't need to do this step, we know the area of spreader and we know the area of TG.
Yes.
So we can get how numbers of TG over the spreader. And
We
so,
already know it's 3 TGs.
okay. So you can calculate the total heat flux come from this surface.
No, but it's not accurate. The flux is coming from only a small area.
Yes.
You want to separate it on the spreader or the bottom of the spreader? No, that's not correct. Okay, now I separated the 3 surface area of TEG. Before going to the meshing application, there is an option here called shared topology. This by activating this option, It makes sure that it calculates, it merges the surface at intersection in the single bond. Between the heatsink and spreader, there is a surface. So it merges this surface to be single one. There is no surface about heatsink and another one on the spreader. It's one. It shares, as its name, it shares the topology.
About the imprinting you did last time.
Yes.
Yes. This, he only made a face or a body shows the thickness of.
No, only a face. I don't need a body. I did this before. Actually, in my work, I did what you are saying, but it's not required. You can only do an imprint.
I can draw all the surface in the back
Okay.
and draw on it three surfaces.
This is easy way using a print is the easy
I
way.
can mix these surfaces on this surface.
I think it's
and-
possible, but projection is easier, I think. But I didn't try this option to draw a surface on the surface.
What I want to know if I should make projection to make a link between this surface and the surface of the heatsink, or if I find it as a surface between four edges and define inside it the value of heat flux, it will work.
You will define a surface like a 2D. I didn't use.
Yes.
I didn't try before defining a 2D surface this way. How it will work? How it will work? I don't know. I never defined a 2D surface in a 3D model.
I think
I don't use it at all.
It's called the surface.
I didn't use it ever.
You can sketch anything in 2D and make a surface. It will be.
I didn't
2D.
try. I didn't try.
I don't know.
You mean using this option, surfaces from edges?
Yes.
I didn't try it. I didn't try it ever in 3D modeling. I don't know how to. Okay. After sharing topology, you will find that most of options are disabled. This made me panic before. I didn't know what happened. I thought the program was corrupt. So all options are. So if you want to do anything else, you decided to change anything, just delete share topology or deactivate it, then do it, then activate share topology. Share topology is the last thing to do. Okay. What else? Okay. Now I've changed things here in the modeler. You don't have to close the modeler because we will come back to it. So you go to the workbench, right click on mesh and refresh. This way you send the new modification to the meshing application. You don't have to close the modeler every time and reopen it every time. Okay, it's to save time. Now we have the meshing application. We will start by the general settings of meshing.
We will need the open.
Yes, no
We
problem.
go for mesh, no problem.
No problem at all.
Using refresh.
The problem happens if you are using the meshing application and open the field. Some problems may occur, but the modeler and the mesh, you can open them
In this
easily.
case, if we make some of the modifications in the VM,
Okay,
it will send.
you have to go to the workbench and click refresh on the mesh here. By clicking refresh, you will get all the new data. Yes. If there is a change in something big, like creating a new body or something like this, you have to change the setting and fix it. But if something small changes the dimension or something simple like this, you don't have to do anything else. Just update the mesh and it will be created again. Okay. The general setting of the mesh, I only change here I make sure, of course, the physics reference is CFD and solver reference fluent, and change the global sizing. Here's the global sizing. I put the largest possible size I will work with, not the minimum. The minimum size I will define it for each body alone. But here I put a general big size for which I will not exceed. Okay, so in this case I will choose 5 millimeter. Okay, I can choose the units here, millimeter, so 5 millimeter. This is a general size, general maximum size for all elements and all bodies. Okay. Now here I want to show you something. I am hiding here all heat sinks. I will start by meshing the solid. Solid domain is always easier because it doesn't have you don't have to create inflation for boundary layer. So yeah, solid is easier always. The problem is this body. Is it regular shape or irregular shape? It appears to be regular, just a cuboid. But the problem is with these faces. These faces, this is the intersection between the spreader and the heatsink, and these faces are for the thermoelectric generators. These faces makes the shape irregular. When creating the mesh, it has to follow these edges, which is in the middle of the shape. So the meshing application can't mesh it. Can't mesh it in a regular way. If I try to create a mesh here, right click on the body and generate mesh on selected body. Look at the mesh, all triangular. This kind of elements called tetrahedrons, which are triangular shape. The shape is very, to your eye, it is very simple shape, but the meshing application can't do it right, can't do it in hexahedrons. It uses tetrahedrons because of these small shapes. This intersection caused the problem. There are two solutions. One I used before, and most of my work was using it. I created another body. I cut 3 bodies between these surfaces, between these two, between this and this. I cut a body in this region, separated it from the heat spreader. Do you know what I want? What I mean? And repeated this for the 3 regions. For this part, I separated this region to be a separate body, and the same for this. This way, the body surrounding all 3 can be treated as a regular shape. But this solution, you don't have to do this. There is an option here called multizone. You select the body.
With the same material.
Same material, same everything.
And you should define the interface between the
No, because
body and
they are a single part. I collected them in a single part, so this I don't need to do this. It's done automatically. I separated. Regular shapes are meshed with a method called sweep. This is the default sweep mesh creates when a shape regular like this creates a mesh on one surface, very regular mesh in the form of rectangles. Then take the same mesh and copy on the other side here, the same mesh. Then connect the 2 meshes together. This is called sweep. This is called source face, and this is called target face. Okay? The problem is we have like a surface here. So the meshing while connecting the 2 surfaces to each other, it meets this face. So the connection is corrupted. So sweep doesn't work. Okay? What I do, it's a method I used before, is separating this region. Now we have 2 bodies, the big one and the small one. I don't use a sweep. I can use a sweep, but not from this face to this face. I use it with the upper face to the bottom face. These 2 faces has nothing interrupts them. Do you know what I mean?
Yes, I mean.
And I use this face for the smaller body as a source face for the smaller body.
I think anyone can work for the small part.
What?
For the big part, you must choose the upper and the lower.
Yes, yes.
But in this small part, you can choose any.
Yes. This is a technique, but it is very needs a lot of steps because you need to turn it back to the design modeler to separate this region in a different part. But there is an option called multizone. Multizone do this automatically. It analyzes the body and it decides that we can separate this region and mesh it separately from this. Do it automatically. I don't need to choose anything. I just click on the body at all, the whole body, and say click insert, like here. Right click, insert method, and choose from method multizone. and leave everything default. Now when I create here mesh, right click, generate mesh on selected bodies. So we have the surfaces here still exist here, but the mesh is regular. So multi-zone saved me a lot of time. But of course I defined in the general setting, I defined that the larger element size is 5 millimeter, but 5 millimeter is very big for the spreader. So I will choose the spreader, right click, insert, sizing, and put here like 1 millimeters for the spreader. And repeat the step again, generate mesh on selected bodies. Okay, this is not a problem. Someone saw this with me before and told me that you have a problem in your mesh. No, this is not a problem. This mesh is very good. Okay, now we have a very good mesh for spreader. When you create a mesh, don't click on generate mesh. Generate mesh will create a mesh for the whole domain, and you are still building your mesh for one body at a time. So clicking generate mesh will take a lot of time for no reason. You just click on the body you are studying and generate mesh on selected bodies. Now we'll go for the next body.
For the next one, I want to ask about you said if we separate the one body into bodies, we have to select the surface started and the target.
Yes,
How this option?
it's work like this. You can click on right click here, insert method, and choose sweep. Then you will find here automatic. Automatic it will try to decide what the best two surfaces. You can choose manual source and manual target. You can choose only the manual source and define it. It will predict the target because it is on the other side. Or you can choose box.
Or you can choose automatic.
And it will decide, but sometimes it fails, so you need to choose. Okay. Since I added a new step, the sweep, the mesh, its color is changed because I added another option, so I need to create it again. Now I need to create a mesh for the heatsink. Since the heatsink and the spreader are in the same part, I measured in the same part, the mesh created on the heatsink will follow the mesh beneath it at the spreader. So I click here, generate on mesh and selected bodies. The mesh is good, it hexahedrons, but its size is very big. So I can add sizing for the heatsinks. Insert sizing, and choose here 1 millimeter. Then select the bodies, generate mesh on selected bodies. Okay, now we mesh the solid domain, no problem at all. Okay, we need to mesh the fluid domain. I will hide all the solids by selecting the part of the solids here, hide body. I will show only the fluid domain. This is the fluid domain I want to mesh. Do you have any suggestion? This shape is irregular, so I can't use normal mesh. I can't use sweep with it.
Multizone.
Multizone, yes, multizone.
How we can use multizone?
That's simple. Just click, insert, and multizone.
Select multizone, generate.
What will multizone do? Well, multizone, as you can see, this is the space between the fins of the heatsink. So these 5 regions can be treated as a single bodies and swept. Use a sweep with it, and the same for the big space above. Can be. I will not divide it. Multizone will do it. I say multizone do it for me. Yes, but for simple shapes, this shape can be divided into simple bodies. But if the body is very complicated and can be divided, multizone will not work.
So what is it? Can be work in two?
I don't think so, but you can try. I didn't try. So I click here, insert. Sometimes, if I right click here, I can't find insert. So you just click on the mesh and right click again, you will find insert. Okay. Insert method, multizone, and define sizing, insert sizing. I will use maybe 2 millimeter, 2.5. I don't want it to take too long. Then generate mesh and selected body.
Why you deselect?
What?
Why you deselect?
Eh? Highlight takes GPU power. So I just reduce the load of the
You save
of the
some
mesh.
more. Another thing.
I don't want the PC to get hot.
Okay. It's very expensive, so you need
Okay. Multizone takes time. If the body is complicated, multizone will take a lot of time. This is the mesh. What do you think the problem with it? It is hexahedrons, no tetrahedrons at all. And you can see inside the mesh, you can use the section here, new section plane, and cut like this, and click here on the section and activate this option. Now you can zoom here, you can see the inside of the mesh. And you can move the section by clicking on it, then selecting this option. You can move and see the mesh inside. So as you can see, the mesh is very regular, no problem at all inside the mesh. You must do it all the time because sometimes the mesh from the outside looks good, but inside it is very bad. So as you can see, the mesh seems good, but there is a problem. What's the problem here? What do you think?
The interface between the fluid and the solid.
No, not the interface. The mesh is not very fine in this place. This is a place where natural convection will occur. Do you think this mesh is fine enough in this place?
No.
The problem is that if I want to refine the mesh, I will decrease the size of the sizing here of the whole fluid domain, but this will cause a problem. This region, this part is very far away from the heatsink. I don't need a fine mesh in this place. So this is a problem. There is a region I want it to be fine, and the region I want it to be fine in the same domain. So I can't separate this. I can't tell it body sizing in this region big and this is small. No, can't be done with multizone.
Edge sizing.
Can't be done by multizone. Edge sizing will do the following. First, it will cause the program to fail, the multizone to fail, or it will ignore it. Because multizone uses sweep. It uses inside it uses sweep. So it starts with a mesh and connected to the other side. So if it is fine on this side, it will be fine on the other side, whatever happens. Okay?
So can make this large body into small zones.
Yes, that's the solution I used. I don't. Okay, all of what I'm saying here is my. I tried and things and didn't succeed. So if you have a suggestion, tell it. Maybe it's right.
That.
Yes.
That.
Adaptive. لا دي في الفلوينت. This is in fluent. Fluent itself has adaptive mesh. I don't know adaptive mesh in here. So when this happened for me, I did the following. I separated a small region here around the heatsink. Around the heatsink here, I separated a small region so I can use a body sizing very small for it. Then the larger region, I use it a bigger size. Okay, this is what I tried and succeed. So I will get back to design modeler. I will remove shell topology. Okay, and I will draw a rectangle here. Rectangle here on the same surface of the spreader. This is supposed to be the sketch of the heat spreader. I used it to create the heat spreader. I will create another sketch for to cut through the fluid domain. Okay, so I selected. I will click here to create a new sketch. Then I will choose rectangle. Then create here a rectangle. And for the dimensions, I will no. I need to create the dimension between these two lines. So I click on this. It gives me an error because the length of this line can be changed. I press OK, then right click, select pair. Select pair, it allows me to select another thing to be related to this line. So I select pair, then I select this line. Now I can have the dimension between the two lines. Okay, I give it like maybe 10 millimeter. Repeat the same step here. Now we have a rectangle here surrounding the heat spreader. I use this rectangle, this sketch, to extrude, but this time I choose, instead of add material, slice material. I want to cut. I don't want to create another body, so I make a cut body. So slice. The spreader is 5 millimeters. The heat sink is 35 millimeters. So I need to create this slice to extend more to surround the heat sink. So I will make it maybe
double size.
50, maybe 50 millimeters is good. I say all bodies. No, I don't want to slice through all bodies. I want only to slice through the fluid domain. So I choose any selected bodies and select this body, apply, then generate. Now we have a fluid domain surrounding the heat sinks, small fluid domain surrounding the heat sinks, and another big domain surrounding all of this. From experience, I think you should also cut a small region here. Do you know what I mean? To be a small cuboid in this area, and another cuboid here, another cuboid here. Do you know what I mean? I will do it.
But if we use multizone from the upper surface,
You can work multizone, but what?
Slice material.
I will slice to separate. I will show it to you so you can understand what I want to do. I want to do here, create, slice by surface. Slice by surface. So I will select this, not this one. You can see it? The top surface of this small surrounding. Okay, apply, and the body which I will slice, this body. Okay, now generate. Did you understand now what I'm doing? Slice is like a knife cutting through material. This way I can do sweep for this. This is a small regular shape with no irregularities at all. So I can use a sweep with this. I will do the same on the other side. It is done already. I will do it for the depths in this direction, Z direction. Create, slice, and select this face, not this. This face, apply. From the bodies, I will select this body, then generate. The upper and lower. No, I can't do two slices at once. I have to slice by surface.
You can send it to surface?
No, we can't. Slice is done by one surface only.
Use one each.
Yes. I will repeat this again here. Create, slice, and select this size, this surface, then this body, then generate. Now I have 5 regular shapes I can use sweep with. I could have used multi-zone with all of this, but sweep is better because it will give me more control. In sweep I can give it bias, you know bias. I can give it bias in this direction, in this direction. So I can increase the size of the elements away from the heatsink. It will give it only
So
for
you do all this in order to make a more to be more control.
yes, to give me more control.
But it's available to use multi-zone with
Yes, it is. If you have no problem in the mesh will have the same size on the whole region. If you have no problem with this, okay. But now I can make the mesh little bigger at the end, smaller near the heatsink. So using bias is good. It will save some elements.
Okay.
Can decrease the elements furthermore.
So for slice, I first choose the surface.
Yes.
And then choose the body
Yes.
that I want to cut.
Yes. Now after I did this, we have, as you can see here, new bodies appeared. These all the bodies of the fluid, because it's now it consists of 6 bodies of fluid. I have to select them and form a new part. I will call it fluids. I do this to share the mesh between them. If I didn't do this, the mesh will be separated. Okay. So these are the fluids. These are the solids. I will call them solids. It's better practice if you have a big model to name everything you do here. As you can see here, that is the extrude of the spreader, the plane of the heat sink base, the extrude of the heat sink. Each step is named to because if I want to do any modification, it will be hard if I have here like 20 steps. I don't know what is done for what. So naming every one of them is very important. If you want to rename, these are 6. All named the same name because they are created from the surrounding. So they are named by the same name. But if I want to change it, it will be very difficult to change one by one. If you have a lot of number, it will be difficult. So if you select all of them and select rename, I will and choose any name if you want and press OK. It will rename it and give it a number. So it is better to know the number of each region of them. Okay? It's useful if you have a lot of bodies. Now I activate shear topology again, generate. Since I did some modification, I will go back to the workbench and select refresh. Then go back to fluid. Now I can use the multi-zone body was the big surrounding of the heat sink. Now we cut it into six bodies. So you have to make sure that the multi-zone is selected for the body you want, because maybe it is assigned to this body, not this, because all of this was 1. Now they are 6. Now so you have to check here for multi-zone which body is selected. It is this, so okay, everything is okay. Body sizing, as you can see here, body sizing is selected for this body. This is wrong. I don't need body sizing for this. I want it for this body. Okay, I will change the element. Now I can decrease the size. I will make it 1.5 millimeter, and it will not affect the mesh of the outside bodies. Right click, generate mesh on selected body. Now we have relatively fine mesh. I can refine it furthermore, but to save time and power, I will not do it. You can decrease it to 1 millimeter.
Okay.
Now we want to add inflation. Okay, we now want to add inflation near the walls of the heat sink and spreader. Okay. When you use multi-zone, you right click on it and select inflate this method. Okay. You will find here that the geometry selected is one body. This is the body which the multi-zone is applied on. So I don't need to select it again. Now I need to select the boundary. So I need to select all the faces of the fluid which are adjacent to the solid, which are these. I will not select this surface. This will be inflated. But now I am inflating the body related to the multi-zone. So I'm selecting only the surface in this body, not other body. Okay? Make sure you don't miss anything. You can click and drag while holding control, so it select all surface. But drag slowly. Sometimes if you drag very fast, it will miss some surface.
Oh, the first one.
First heatsink.
First.
Now we select all the surfaces which will be inflated. I click apply. I will leave this at default. You can do a mesh independent test later. Now I'll create again the mesh on this body. Inflation will increase the layer besides these surfaces to capture boundary layer. Well, inflation used for boundary layers. That is the main. Of course, you can see it from here because this is the surface itself. You can, to see it, you will use the section plane I created earlier. As you can see here, this is the inflation layer. The mesh here is regular with the size of 1.5 millimeter I already defined, but besides the wall, there is another additional refined layers to capture boundary layer. Of course, you can increase this number by increasing the number of layers of inflation here. I here defined it 5. If you want to increase it, just increase the number. And here is this is the outer side of the heatsink, but also has inflation layer. I want to hide these bodies so you can see it better. I can move here the section so you can see the formation. This is the layers above the spreader in the region where there is no heatsink. Can move it.
This is called the ICM prism layer.
What is called the prism layer?
This inflation called in ICM
Ah.
prism layer.
We have a problem here. The mesh here is very big. Because of this surface is the heat sink has 30 millimeter thickness, 3 millimeter thickness, and I defined the body sizing for the whole surrounding at 1.5. So it put 2 cells at the thickness of the heat sink. Only 2 cells at the width. Okay, this is a very large, considered relatively large. So I want to increase the sizing at this face. I can do face sizing for this face. It will the body sizing for the whole surrounding will be 1.5, and at this face I can decrease it a little more to make it maybe 0.75. Okay, so I will select the faces. I will disable the section plane first, then select these faces. This is the faces which are the fence tip, Then insert sizing. I will make it 0.75. Sometimes multi-zone takes 10 minutes working if the geometry is complicated, so give it time. Now let's look again at the. As you can see, this is better. This is a lot better. I want to choose this region from above. As you can see, because I told you that multi-zone works like a sweep for a smaller region. So because of the mesh is fine here at the bottom, because I created a 0.75 millimeter sizing for this face, you can look at the other side and see the effect here. Because the faces are meshes are imprint on the other face. But this is not a problem. This is good. This is very good mesh. So now this region has a very good mesh. The inflation, I'm using here inflation with multi-zone. So I click on the multi-zone method and select inflate this method. By doing this, you will get the inflation option here. And and you will find the body which is the multizone used with is already selected. You will find that the body is already selected. You don't really need to change this, but only you have to define the boundary by selecting the faces which will be inflated, or additional layers will be added.
So I have a question regarding the mesh quality. For instance, yes, in the Kawara, Professor Kawara suggested that when the formation usually meshing is not a sign of good mesh, but you suggest that this one is a good mesh.
Deformation, this kind of deformation is not bad. Deformation like something very skewed or very small angle, very large angle, but this is not here the case. And if it occurs in one cells, two cells, this is not a problem. The problem is when it occurs in a critical part and very large number. This, and you can see this when trying to solve, you will find that the solution diverge. In Fluent, you can check the location of the divergence. You can check, you find that the divergence occurs in a specific region, so you recheck the mesh. If you find the mesh is skewed in this region, have very aspect ratio, has very large angles, then the reason is this mesh is not good.
That's what I wanted to answer. Is there a mesh quality? How do I know mesh quality?
I can see something. It's rough. It's not. It's not like a number. You see it. You say the mesh is good or bad. It's relative. But here you can, by clicking on mesh, you will find here something called quality. You will find that here I can. No, not this. Mesh metric. Yes. You can find the element quality aspect ratio is very important. This is the length to the width of the element. It shouldn't be a very big ratio. So if you find that the aspect ratio here, if you click it, you will find the minimum, the maximum, the average. The average is 5.8. That means most of cells has good. But there are maximum 23. 23 is very bad, but not a lot of cells have this problem. And in Fluid, this is expected near the wall, because we need very fine mesh near the wall, but in the flow direction, we don't need it to be very fine. Do you get it? So it is a little accepted near the wall to have a very big aspect ratio. So it is relative. I think you can check the location of these cells by clicking on the. Yes. By clicking on this, when I activated aspect ratio, I get like a bar graph here. I can click on here's the number 12, I think, or 14. By clicking on it, I can zoom and find the cells. Where is the location? As you can see, it is only at the wall, which is accepted to have a very big aspect ratio near the wall. But this is here I have a very big aspect ratio. Maybe I click on it and see where it is. Yes, those are the elements that have big aspect ratio. Again, not only 5 elements. Will not cause a problem. If you solve it and found a problem, a divergence occur, you will know that this is a problem. Okay?
I think that the total till 30 is acceptable. The aspect ratio till 30 is acceptable.
One is the best. One means that all elements are square. It is very good. But we can't achieve this.
Yes.
You need to decrease the width or the thickness near the wall to capture boundary layer. But you don't have to decrease the height, because the variation of parameters in the flow direction is not very big like in the boundary layer direction. And in my case, I did some modification for the film. There is a location in which I get a velocity while solving 23 meter per second. This is impossible. This is natural convection. It will never reach this kind of value. So I know this is the location which have problem in mesh. So I tried to fix it. Okay. Now I completed the mesh of this region. I will try here generating a mesh. I didn't here insert a sweep. I can insert sweep, but I will try meshing without sweep. Okay, here is the mesh. The mesh is dependent on everybody, since this body and this body are part of one part. So the mesh is here is dependent on this. This will be dependent on this. So this automatically the program created a sweep for this region. I don't need to create a sweep for it. But I will do this if I want to control the sizing furthermore. If I want, I maybe try this here. I will click insert method and choose sweep. I don't need to select the manual source, because the source will be for sure this already meshed surface. It can't create a source from another surface, because we have already meshed the surface. I can here define the number of divisions, which is in the sweep direction. Only the sweep directions we can control, or we can define element size. Maybe define element size here to be 4 millimeter. I can define a bias. If I choose this means the size will start smaller and get bigger. 4 millimeter is the average of the minimum to the maximum. It has an equation like this. If we have the mesh here very small and here very big, so if this 1 millimeter and this is 4 millimeter, the average is calculated by this square root 1 by 4 equal to. So if you want to get this dimensions, you define the sizing to be 2 millimeter and then choose bias 4. 4 is the ratio between the largest to the smallest, and the 2 is the square root 1 by 4. Okay, this is how it is calculated. We define for the bias, define element size and bias factor. Bias factor is the ratio between the biggest to the smallest. This is the bias factor. Okay. The element size to exist equals square root the largest to the smallest. Multiply by each other. So if I want to get 1 millimeter here and 4 millimeter here, I don't define 4 millimeter size. I define 2 millimeter size. So that square root and bias factor 4. So square root 4 by 1 equal to. Okay.
So if I want 1 to 3.
1 to 3, bias factor is 3. Okay? Square root 1 by 3. Then the element size should be defined. It's 1 to 3. There is an error. It now worked. I don't know why it didn't work before.
It's a sense.
It's sensitive. As you can see, the inflation, I don't need to create new inflation. Because sweep, as I said, it takes the same mesh on the surface and copy it on the other side. So it copies the inflation with it. If you look on the other side here, inflation is already there.
But you didn't use the bias here.
I can
Because I
activate.
see
Yes, I didn't activate bias.
a sudden enlargement in the mesh.
Yes.
Space.
Yes.
There is no smooth.
I didn't yes, I didn't activate bias. I will activate now. I hope it works. I will in meshing. The sequence of meshing is very important. So we mesh only this first, then mesh this, because this is dependent on it. I didn't select both of them and create generate mesh. Select this first, generate, make sure everything is okay.
Bias over this bias.
This body.
Why this?
I don't know why it requires a remeshing. I don't know why. I hope it works. Finger crossed. Is it okay?
I will check the transition. There is no transition.
It is getting smaller, getting bigger.
Which option did you select?
I select bias.
Bias.
The bias shows the shape. As you can see, the line here starts small. The second one starts small, then gets bigger. This is how.
Okay, and we can repeat it for the other.
Yes, I can repeat this for this body. Bias here, then bias there, and okay, here. I will not create sweep now for now, but you know
Is
the
it bias for the body size or for what?
bias for this body. For sweep inside the sweep option.
That's a sweep
Sweep, yes.
option.
Yes. Okay, I can create mesh here and here, then here. Okay, or I can create here first. It is better to create a mesh in like a sequence. The body, then the body next to it, then the body next to it. So since the mesh is already created here and here, and here, then I create here, then here, and here. It's like a sequence because everyone is dependent on
I
the
think
side.
for the other thing, the third part, the sequence is not matter in this case.
Maybe you could try and see, but it's very effective. If I mesh this first body this, then try to mesh this, it will fail because it can't achieve. This body will have big element size, but this body will have small element size because of the small spacing between the fins. So the multizone will fail to achieve to start from a big size and sweep on the small size. So it will fail. So we always mesh the part which has the more problem. If we succeeded in doing it, it will be easier afterwards. Okay. Now meshing on these bodies. Now everything is okay. We have complete mesh. Okay. These bodies we can control them better by using sweep. Also, this body will be swept from this surface to this surface. We can create the bias to get larger away from the heatsink, and this body can be swept from this surface, bottom surface, to the upper surface, and can use bias to get it larger away from it. These two bodies will follow. We will follow these two sides because this is already meshed. This is already meshed, so I don't need to choose bias. Understand why?
It will be automatically meshed.
Because it must follow the surfaces which are already meshed. So the surface on the right, this surface is already meshed and have bias in this direction. This surface is already meshed and have bias in this direction. So the body here will be created with bias in this direction and this direction without creating sweep. We don't need to create sweep in this way. It will be done automatically. Okay?
But I want to make a sweep.
For this, no, it will fail. Because the sweep starts from a surface to the other. It can't, while moving in this direction, it can't have another constraint on the side because it has a mesh on the other side already meshed. So using the default option, we'll try and do both to follow the mesh at the bottom surface and follow the mesh at the side surface. So it will work without using sweep. Okay. Now as we are creating the mesh, we use steps. Created mesh here first. Created mesh here, then here, then here, then here, then here. Okay. If I changed something and try to create dimension as an example, I want to redo these steps. This will take a lot of time to go every time and go create mesh on this, then create mesh on this. So this will take a lot of time. So you can record the sequence of meshing. So whenever you change something, you just click generate mesh, and it will follow the same sequence. Okay? How to do this? By after making sure that everything is fine, you know the steps, you did everything, every setup, settings, all settings here are done correctly. You clear the mesh. by right click here on mesh, then clear generated data. Again, right click here, clear generated data. Now we will cleared all the mesh. You will find something here called worksheet. Activated, you will find something called start recording. You click on start recording. Now the meshing application is recording your steps in the sequence you will do, and save it here. Because and every time you go back to the measure, you will generate mesh and it follow the same steps. Okay. So now at first we created mesh for the spreader.
You forget solid.
This is the solid.
This is solid. Okay.
Yes, I selected the spreader. This is spreader. You can go to the worksheet. You can see meshing 1. This is the first step, and it's still recording. I go back here and select. I will hide the fluid for now. I will select the 3 heat sinks at the same time because they are not dependent on each other. Then create mesh for the heat sink. Now I will go to the fluid. Generate mesh of selected bodies. After you finish this, I will say it quickly. After finishing and recording all the steps, you will see all the steps recorded here in the worksheet. All the steps will be recorded here. If I want a mesh to be created, I will click generate mesh. I don't need to do anything. The steps are recorded. I will click generate mesh. It will follow the same steps.
Generate mesh worksheet.
No, I don't have to enter the worksheet. The worksheet only to check if the steps are there. But I don't need to go back to the
So
worksheet.
when I finish, I click stop recording.
Stop recording will be clicked automatically. You don't have
If
to.
anything is changed and use the generate mesh,
It will follow the same steps.
But just wait and
But you have to finish the steps. I didn't finish it here.
Okay.
When you finish the steps, if everything is okay, you will find this stop recording is clicked without clicking. You will not click it. It will be activated automatically, and this will turn green. Okay? And you can, if the mesh, if the steps are wrong, you found something wrong, you can delete all steps and start recording again. As you can see, after finishing the mesh, the start record it turns to start recording. It was stop recording before because it was recording your steps. Now it finishes the steps because the mesh is created completely. So it this turns green and all the steps are created here. Now if you want, you can change anything and click generate mesh. It will follow the same sequence in creating the mesh. You don't have to create it one by one. Okay. Now since we have 2 parts, you will find an option here. This will not appear if all bodies in the single part. This will not appear. You will find this empty. But since we have 2 parts, it will create automatically a connection between these 2 parts. If you open them here, you can click. It created 3 contact regions. If you click on any one of them, you will find the contact. You will see here in the solid part of the contact, and if you look here, where is the bodies? This is the fluid contact of the between 2. We have 2 parts, one for the solid, one the fluid. So if when you click on the contact region, you can see the interface surfaces in the solid region and the fluid region. Okay, as this is one. The second one will be between the first heat sink and the fluid region. This is the second one. This is the third one. It's okay to continue this way. The fluent will automatically take this contact region and create the interface for you. You will not do anything from your part. Okay, but sometimes the contact region have some issues with it. Instead of creating 4 contact region, you may find them 6, 5. Another illogical number. It divides one region to 2 contacts. This sometimes causes problems in fluent. So if you clicked on each contact region and see that the contact region is defined correctly by examining them here in the 2 windows, you can continue. If you think there is something wrong, you can disable them and create surfaces with any name you want as a named selection. You know named selection? Okay, I will show you both ways. I will suppress them. Right click and suppress. Now I will not take the contacts, the mesh created for me, the meshing application created for me. Okay, I will create named selection for these interfaces with the names I want, because this way I can recognize them better in Fluid. Okay, so I will create first the contact region between the spreader and the fluid. So I will click here and hide the fluid, then select the solid region. This is a solid surface in contact between the solid and the fluid, between the spreader and the fluid. This is the solid side. So I will click here name selection by pressing N, or right click and create name selection. Okay, so I give it name spreader solid. This is solid part of the interface between the spreader and the fluid. I press OK. I can create the solid part between the heat sink, the first heat sink, and the fluid. I will click all surfaces. I think everything is okay here. Okay, place N, H is 1 solid. This is the solid interface between the heat sink, the first heat sink, and the fluid. Okay, I will repeat the step for the second heat sink. And this final part. You can see a list of them here. Which is solid 1. There is something missing here. I can edit, of course, the name selection. This one is missing some faces, so I click here and continue selecting the other faces. Okay, this one is okay. Now I have the solid side. I need to define the liquid side. So I will hide the solids and show the fluid. Where is show? Okay, okay. For the surface between the fluid and the spreader, this is supposed to be the fluid side. So I will name it SP fluid. And this is the first heat sink. I just click on them here to see a number of faces, because if everything is correct, there should be 21 faces. This is a way to prove to correct you if you are wrong. Now we have the liquid side and the solid side defined here. Okay. That's it. We continue to fluid.
Only mesh name selection.
Yes.
Yes. Is it possible to select all the surface and limit one?
One interface. It is better for post processing when you want to calculate heat flux at one heat sink. So this way I can just click on. I will find an interface with the name of the first heat sink, so I can click on it and get the heat flux. If you select all these interfaces in a single surface, you will find it defined in Fluent as a single surface, so it will be harder to find what you want. Of course, we need to define bodies for each zone. For the name of zones, will be used in Fluent. So I will define all of this as fluid. Create name selection, fluid. I will hide the fluids and define a name for the solids. This will be the spreader. This will be heatsink 1, heatsink 2, heat sinks. Of course, you must define some faces for the outlet, for inlet. Okay, we have time. I need to say something about this. Okay. What is the boundary you think I will define? I need
think the symmetry boundary condition,
of course, these sides, as I said before, these are symmetry. This side symmetry, and this is symmetry wall. So let's define them. Those are easy ones.
and I think the far one is the pressure outlet.
Okay. Pressure outlet. Is there outlet flow from them? So is it okay to?
You have select
What? There's something wrong? Oh yes, sorry. I selected this wrong. Okay. Okay, I think this is correct. This is symmetry faces. Okay. What do you think other faces? This will be adiabatic.
Yes.
I will call them wall or adiabatic wall. Okay. This is supposed to be the TEG1, TEG2, TEG3. Okay. What about these surfaces? What will be their definition? These surfaces. What?
Vent
What do you mean by vent?
is an open area that can the flow go out or go in.
Yes, this called an opening. But in Fluent, how to define an opening? A surface which allow both flow in both direction, and for opening as a physical meaning, the flow if going from the outside to the inside, it should have a static, a total pressure equals ambient pressure. If the flow is going from inside to outside, it should have a static pressure equals ambient pressure. So how to achieve this pressure outlet? As Ahmed said, pressure outlet is the only option that allows this exactly. If the flow was going inside during solving, it will assign the total pressure as ambient pressure. If during solving the flow was going outside, it will assign the static pressure equals to the ambient pressure. I'm trying to explain it in the physical meaning, not because of Fluent says so. In the physical meaning, when we're studying something, when we have a space in which there is a flow, when the flow is going outside, like a water table, the flow is coming of the water table, the flow adjusts itself so that its static pressure equal to the ambient pressure. Because if anything else, if the pressure is higher, if the pressure of water is higher than the ambient pressure, this means like the flow is coming very strong, so its velocity increases furthermore because there is no equilibrium at this surface. But to achieve equilibrium, the flow will keep increasing its speed until its pressure adjusts itself to be the same as the ambient pressure. So the flow coming outside of the pipe with an equilibrium state. So the flow, which when coming from the inside to the outside, it adjusts its static pressure to equal to the ambient pressure. Yes. But if the flow is coming, coming to me from the outside, it's coming with its own energy, which equal to the total pressure. Total pressure represents the total energy of the flow. Since it's coming from me, it has to sacrifice, because I'm sucking the flow. I'm sucking to me, so I'm not the source of energy. It's coming from its own energy. So it's sacrifice part of its energy by decreasing its static pressure, converting it to dynamic pressure. So we find that static pressure is lower than the ambient pressure when the flow is coming to me. So the total pressure is equal to the ambient pressure because it's coming from the ambient. This is all of this done by defining the flow, the boundary as a pressure outlet. You don't need to define it. Define pressure outlet, pressure inlet. And during solving, you will find an error, not an error, it's a warning, saying reversed flow. Because the flow, its name is pressure outlet. So whenever flow coming inside, it warns you because it thinks you made a mistake. But there's nothing wrong, no problem, no.
I found it on my run and something
That is different
Too much.
from the case.
Yes.
It is noting
Please.
natural.
I think this one is the liquid process. I think this one.
I don't know your case, so I don't can judge. Another problem will face us here. Your problem another time. My problem now. Another problem here will happen if you define this pressure outlet and you define the pressure. Or he will ask you about the ambient pressure. You give it the ambient pressure 1 atmosphere, or you put it in the form of gauge pressure, so it equals 0.
Yeah.
This is cause a problem because when you're studying natural convection, this small height has effect on the pressure because gravity. So when you go higher, the pressure is supposed to be lower. If you didn't consider this and put the pressure on this vertical surface as constant equal to the ambient pressure, this causes a problem. You will find that the flow, the pressure here is supposed to be low, and here is supposed to be high.
Could we reduce it?
If you set the pressure equals 0 gauge, pressure constant, you will find the flow coming, going down,
Yes.
going down here, without any effect, without even putting any heat from there. The flow is going down because it is defined, yes, due to gravity.
Gratis. Yes.
Due to gravity is going down, and the pressure you are assigning a constant pressure here, which is
So
abnormal.
we should
So
use
you must define a pressure varying with height.
Using UDF or what?
In the nuances, you don't need UDF.
Okay.
The nuances, you can put an
and
equation.
you can get this this equation
P equal
project H.
rho G H. Negative rho G H. Okay, so H is the height,
I mean,
rho is supposed to be the average density of air.
this is a gauge version. Okay,
What?
this is a gauge version.
Yes, average.
Yes, yes.
Okay. Rho is the average density for at ambient condition. So if you are studying at 25 Celsius, you will find rho at 25 Celsius.
G.
Then G is the gravitational acceleration, 9.8. H is the height. If you didn't do this, you will find the backflow going down.
And even with the upper and lower surface.
Our surface will contribute to this. You will find flow coming from here,
Yes, yes.
going there. Because you are defining here pressure higher than normal. It is not supposed to have a high pressure here. Okay? Because as we can remember from Bernoulli equation, we have P plus rho G H. This is the energy of the flow. If you calculated this for here and here, you will find that this value here is bigger. So the flow goes from the higher value to the lower value. So it comes from up to down,
Yes, yes.
which is not a natural phenomenon. Okay? So you have to define a variable pressure. Or if you can't put an equation, you can increase the size of this domain and define this as a mole.
Okay.
You can increase the size of here is the seed sinks.
You
You can increase this size.
an extension to the.
Yes, increase this size a little more. Okay, and define this part as a wall. Because there is no problem here. There is no flow here. It's supposed to be no flow here. So the wall will not affect the flow.
But you
And you can define this surfaces and this surface are both horizontal. So you can define, you can calculate a value at this height and define it as a constant, negative 10 Pascal maybe, and you can define here a constant 0 Pascal. Now you define the two variable pressure which considers the height, and here, because you can't insert an equation, if you can't insert an equation, you define it as a wall. And it will not affect the solution because no flow here at all. And you can define it if you are afraid of some flow in this area, you can define it as a slip wall. A wall with shear equals 0. So if there is flow, doesn't affect it. It doesn't affect it by the wall. But the best solution, of course, is to define an equation. If you don't have the latest version, you will not define an equation except by UDF. Okay, so I will choose this walls. and select outlet. Okay, now we have outlet here.
How can I add equation?
Using UDF.
I equation in the latest answers. I will show you how to add an equation here. Yes, but I use a UDF because UDF are more powerful.
More
Powerful. UDF allow you to do more things. You are calling someone?
مثلا someone called me.
Okay. When modeling natural convection, it is better to activate double precision. Okay, because it affects accuracy a lot. So now I will show the interfaces quickly. As you can see in boundary conditions, here is the surface that I created for the interface between the heatsink and the spreader and the fluid. I will click on all of them, right click, type, and change it to interface. Okay, selected all surfaces, right click, type, interface. Okay, and enter here.
Mesh interfaces.
Yes, at domain mesh interfaces.
I think it's below the boundary function.
Ah, yes, it is here. It is
The
here.
sequence is doing this.
Ah, yes.
They start with boundary function, then mesh interface, and then
Yes, exactly. You can create them automatic by selecting two of them. This is the interface between the heatsink, the first heatsink and the fluid. I select both of them and give them a name.
HS1 total, I think. Something like that.
Enough HS1.
Yes, okay.
I select a name, give them a name, and auto create.
So what is the difference between auto create and the manual create?
Manual create will let you choose which is the interface side 1 and the interface side 2. If you have multiple surfaces as a side on one side and multiple surfaces on another side, so he allow you to choose what is on the first side, what is on the other side. But auto can choose this automatically. You can define which is which. This is a simple case, so it will not differ at all. Again, HS2, fluid and solid. I will change the name to HS2, auto create. The same here, HS3. And the last one is okay. This is the interfaces created. Now we will have no problem during solving the. If during solving you created a contour for temperature and found that the temperature doesn't enter the fluid remains cold, then there is a problem with the interface. Because the interface is responsible for exchanging data between these two parts. Okay, if you found that there is no temperature transfers to the fluid, then there is something wrong with the interface. Okay, between the solids, as I said before, they are a single part, so I don't need to create interface.
I think there are some interfaces with fluid.
What?
Without your creation.
No, not interfaces, internal regions. These are interfaces I created now. These are interior regions.
Okay. I didn't see it.
Not interface. Now for the outlet, how to create an equation. We need, as I said, we need to define a pressure as function of distance or height. The height here is y direction. So here, as you can see, you have a new option called expression. You can select expression, and you can add another options to see full options or details of the expression. You press on this. Okay. Here, I want the equation to be negative rho, maybe rho 1.225. You have to add units. When adding expressions in Fluent, you have to add units. So 1.225 kilogram per meter cube. Okay, we add the units in square brackets. Multiplied by G 9.8 and the unit meter per second squared. Okay?
Times y, I see.
Y, yes, Y. You can add Y, or if you don't know the expression, you can find them here. Variables.
I think it's f of x.
Y. No. Height is in Y direction.
Okay. After variable which is what?
Variables. There is something called alias. Alias is the most used parameters. You'll find the pressure, temperature, U, V, volume, and you'll find Y. Or you can write Y. Okay? If there is a problem in the units, it will not accept the expression. So you must enter all units.
Why meter or
Meter, of course.
you should write it?
No. If a variable is entered, from here, it's fully defined. You don't need to change it. So Y it is meter. Okay? You don't need to do conversion. It will do it for you. If you have row in another units, but if you give gram per millimeter, maybe it will do the conversion.
So you will adjust the units itself.
Ah, yes. But you have to define units. You can't leave it blank.
You still have to define because I thought maybe you define
What?
gravity.
What is about the?
Do you need to? Because you said anything that has already been defined, you don't have to put units.
Yes. But I didn't define gravity before.
No, when I was at the beginning there.
At the beginning, yes, it is zero. I have to define it.
Okay, you left it.
I left it zero, but of course I will return it and define it to negative 9.8. Whatever I define it there, I need to define it here. I have to define it twice. I think you can define it as the same. I will try. Maybe define single G with 9.8, then use this symbol in both of them. Maybe this is right. Okay, I will try it here, if it works or not. Yes, okay. What Yusuf say, it is wrong if something repeated, like G here, repeated in multiple places in here, in the define of gravitational acceleration, and will be repeated in the equation. You may make some mistake and put it here 9.8 and there at 9.81, so there is a change. So it is better to define G with a specific value than use this symbol in all locations. How to do it? Will have here something called named expressions. This is new in the new access. So you click on named expression, new.
Only in 19.2?
No, this is not 19.2. This is called the 2019 R1. This is the name of the version. This is the latest one. When you set up it, you will find the name in the folders 19.3. But the actual formal name.
You can find G in constants.
Yes, yes, you can find G because I think it's here. It is here. So you can use it. I mean, as a general rule, anything other than G, you have to define it. It's better to define it as a named expression and use the named expression. Assuming that there is no G here, I can define new one. Let's name it GRAV as a gravity, and put the definition 9.8 meter per second squared. Okay, and press OK. Now we have an end expression for gravity. We come here and do expression, and he write gravity. Or you can click here and you will find the expression is here. You can select it. When the unit is correct, if you put anything that has a different unit, it will reject it. It must be meter per second squared. Now when we go to the boundary condition of the outlet, you will remove the 9.8 here and add GREV. That's better because if you change the gravity, it will be affect all other parameters. Okay.
So this method that you just showed us, can we define an equation for inlet? Maybe
Yes.
as inlet.
Yes.
Maybe velocity.
Yes. You can define a velocity profile
You have the
temperature profile, anything, and you can define it as a function of another parameter in the solution. During the solution, you can define the flux as a function of the average temperature at the outlet, maybe, and you can add if condition. You can add if condition if there is something, define the flux as like this, and if something else, define it like some.
And this is not available in 19.2.
No, this is new. This is great.
Available for only for
This is very good. Adding an if condition, and you can define things in, as a function of time, as a function of iteration.
the question.
This is very good. Last thing we need to define also, you have to define the properties of air. The properties of air must be ideal gas. Of course, it can't be defined as a constant density. So it has to be ideal gas. And there's something here called operating condition. In operating condition, you have to define something called operating density. During solving, putting it's a recommendation in the help to put the value here equal to 0. The help, the documentation says this forces the program to calculate the density at every location. Okay, if you left it at 1 point to 125, it will take this as a constant value and ignore that you said it's an ideal gas. This is helpful in a model called Poisson, I think. I don't know the exact name. There is a model, a simplified model for natural convection, which treats the air as constant density at all locations except the location in which there is heat transfer. This is speeds the solution. So it needs an operating density to define the density at these locations, which there are no heat transfer. But if in the model I'm using a complete ideal gas with variable density at all location. So in this case, you have to define here the operating density equal to 0. This doesn't mean the density equals 0. It forces the program to calculate it.
So if we deselect this,
No, don't deselect it.
don't select it.
Select it and equal
If we
0.
don't select it,
This may cause problem there because as you can see here in the console, I don't know if you can read it. It is recommended to use a specified operating density value equal 0. This is a recommendation when you're studying natural convection. It will appear automatically when you define the air as ideal gas with the G have a value. So I define here equal 0, and the density I used in the equation of the pressure was 1.225. This is the density at 15 Celsius. So I define here the operating temperature at 15 Celsius also. If you are defining the operating temperature, this is supposed to be temperature of the ambient. So if you define here the operating temperature at 25 Celsius or 298, use the density of air at 298. Okay? Make sure that you use the same density at the same temperature of the operating temperature. Understand this or what? This is the operating temperature. This is the temperature of the ambient. Okay? I used a density in the equation of the pressure. Do you remember the equation? This equation. This density should be corresponding to the temperature of the ambient. So it's supposed to be corresponding to the temperature of whatever you put here. I put here 288, which is 15 Celsius. The density at 15 Celsius is 1.225. If the ambient temperature is 25, you must specify here 298, which is 25. And in the equation of pressure, use the density of the air at 25. Okay, that's it. This is what you need to define to solve natural convection. Of course, here you must define the flux. I have an equation. You can put it here if you want a constant temperature. Put it as you wish. This is and start solving. That's it.